You guys have been looking at electricity for the last few days, and I want to go through a couple of the labs that you've done and make sure everything is going according to plan and you're understanding things. Now, the first lab you did was, just a basic static electricity lab, and we've talked about this a little bit before, but I want to make sure you understand how you know that these things had the same charge. So you took a pen, you rubbed it through some wool, laid it in the hanger as it's shown, and then you had to do the exact same thing to another pen. You brought the two pens next to each other. Now, this question here says, hey, do the pens have the same charge or different charge, and how do you know? Okay. Now, it says answer based on what you did, not on what you think you know. Okay. Well, they have the same charge, but not because they repel each other. Same because prepared the same way. Right? You did the same thing to both of them, so they should be the same. Okay. And then when you bring them close to each other, they repel, which is good, right? And in general, how do pairs of like charges behave? Like charges repel. Okay, we already knew that. All right, then we did a different thing. We rubbed a plastic pen with wool, and then we rubbed a glass rod with cotton, and we bring them near but not touching, and what happened? They attract, right? They pulled towards each other, which is maybe different than what we think, or maybe it's what we expect, okay? Now, do the pen and rod have the same type of charge or different types of charge? Well, this time they attracted, okay, and so we're going to say different, not because they attracted, but because if like repel, and these didn't, okay, so we know they can't be alike because if they were alike, they'd repel, and since they didn't repel, they must not be alike. So in general, how do pairs of unlike charges behave? They attract. They like to be with each other. Okay. Now, this big box goes through and it describes just what you did. Important things, Q is the symbol for charge, and it can be positive or it can be negative. The fundamental unit of charge is 1.6 times 10 to the negative 19th coulombs. That's the charge of an electron or the charge of a proton. Electrons being negative, protons being positive. Okay. Coulomb is the SI unit of charge. Alright, so we had the rest of this. Rub a pen with wool and place it in the holder. Bring the wool near but not touching the pen. What happened? Hopefully they attracted. Okay? And if they attracted, we know they had opposite charges. And the reason they had opposite charges is because when you rubbed the cloth on the pen, okay, what we got is we got some transfer of charge. And depending on which way this happened, we had charge move from the cloth to the pen. And if you think about that, okay, this thing, the cloth started neutral because it had even numbers of pluses and minuses. But if some electrons moved over, now it's got extra pluses, but those extra pluses are there because the pen gained some extra minuses. So they became charged in opposite ways because charge transferred from one to the other. Okay? Suppose that a glass rod is rubbed with cotton, and so basically we do the same thing. They should attract because charge again transfers. Okay? And when charge moves from one object to another, the first object is going to have a different charge than the other. Okay? As long as they started neutral. Now, rub a glass rod with cotton, hopefully they attract, and yes, this does agree. Okay? So in general, if two initially uncharged objects are charged by rubbing them together, what can we say about the type of charge? They're going to have opposite charges, okay? Because the one transfers charge to the other. Now, this is kind of fun, charging by induction. Okay, so you can rub two things together to get them to charge, but you don't have to. Okay, if you imagine that this is neutral, it's neutral because there's an even number of positive and negative charges. Okay, so negative, 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 negative. Okay, so everything's got an even number of charges. Well, if we bring this charged object next to it, and this has got a whole bunch of pluses, all these pluses right here, they don't want to hang out there, okay? So those pluses are going to get pushed all the way over here. But these negative charges are going to get attracted this way, right? They move over. They're like, hey, let's go hang with these positive charges, okay? And so you can see these charges separated, okay? The overall amount of charge didn't change. They just separated. Now, it says let's go ahead and cut this wire. Gone, okay? If the connecting wire is cut and the charged object is removed, now this goes away, but these can't move back. There's a gap here. There's no way for them to flow. So the sphere A will be negative, and sphere B will be positive. Okay, and this is charging by induction. Okay, it's the separation of charges. All right, now if these were insulating spheres, okay, then the charge can't really move. That's what insulators do. They hold charge. They prevent it from moving. Okay, so neutral and neutral because no charge moves. Okay, that's what it means to be an insulator. Now, last little bit here is some application. An object has a net charge of positive 3.2 times 10 to the negative 15th coulombs. That means it's got an excess of protons because it's extra positive. How many of these particles are there? Well, 3.2 times 10 to the negative 15th coulombs. Okay, and we want to know how many there are. Well, each particle, okay, has a charge of 1.6 times 10 to the negative 19th. Okay, so one atom has a charge of 1.6 times 10 to the negative 19th coulombs. Okay, which means we're going to take 3.2 times 10 to the negative 15th divided by 1.6 times 10 to the negative 19th, and that's 20,000. Okay, so 20,000 extra protons, or you could say it's missing 20,000 electrons. Okay, however you want to look at it. Now, we're going to take what we know about charge and use this one more time. Okay, three identical conducting objects, A, B, and C, are initially charged. Object A is +4. Now, I'm ignoring the unit for now because they're all the same. No charge on B, so it's 0, and -8 on C, -8 microcoulombs. Okay, that's a micro means times 10 to the negative 6. Record these charges in the first row on the table. Got it. Awesome. Now, object B is touched to object A. These are conductors, right? Okay, so if B and A touch each other and they can conduct, positive charge doesn't like positive charge, so these are going to push them away. But it can't push it all over to B, or B's going to push it back. So it's going to stop flowing when they have equal charge. Now, since nothing touched object C, it's still got its -8. Okay, but this 4 is now distributed between A and B. All right. Now, C is touched to B and removed. Okay, so if B and C touch, this one's negative, this one's positive. Now, those attract each other, right? So the positive is going to pull the negative towards it, or the negative is going to pull the positive towards it, however you want to look at it. But, again, if both of these charges, oh, and we'll go A, it's still +2. If both of these charges end up over here, then this is 0 and this is -6. And all those negatives still don't like each other. So some of those negatives are going to leak across. Okay. So if you look at this, you can say its total charge is positive. Nope, its total charge is -6. Okay. And so that charge is going to evenly distribute -3, -3. Okay. And then finally, step C, object A is touched to object C and then removed. Okay. So okay, we've got a +3 or a +2 and a -3, which gives us a charge of -1. Okay, well, what do we do with that? Okay, can we have -0.5 a microcoulomb? Absolutely. Okay, so if both these positive charges go over to this thing, okay, it's going to end up -1 and it's going to end up 0. Well, that negative doesn't like other negatives, so it pushes some of those negative away. Okay, so I'm going to -0.5. -3, -0.5, because the one in the middle never changed. Okay, and so if we add these up, +4 - 8, total charge is -4. +2 + 2 is +4 - 8, total charge is -4. +2 - 3 - 3, so -6 + 2 is -4. And -3 - 1/2 is -4. Okay, and so the net charge always stayed the same. Okay, and that's the conservation of charge. It's just like anything else. We can't create or destroy energy. We can't create or destroy matter. And so the total charge, which is based on a particle, stays the same. Okay, I believe that's where that one ends. Okay, hopefully you got some good results and everything went according to plan. Okay, if you have any questions over that, let me know. I hope everything went well.